So while you're having a look at your exam, I want to draw your attention to the board because I have posted several assignments on active chemistry. So the first one covers the stuff that we've already gone through in chapter 11. And that is due Friday because it's good to readdress this material as soon after class as possible. That helps to firm it up in your mind. The next two are going to be due after spring break. So I'm not going to make anything due in the middle of spring break. And in fact, they're due on the Tuesday. So if for some reason you forget and you don't do it over spring break, then you can still have until Tuesday evening to do it. But because there are two of them and one of them is pretty math intensive, you're going to want to try to get started on them a little bit over spring break if you can. I'm also going to put a, what do they call it? Foundations assessment. There should be a T on assessment. On active chemistry as an assignment. And I think it is in the folder unlisted. Yeah. So the way that's going to work is if you do it, you're going to get credit for it. Everybody's going to get 100% who does it. So don't worry about how you do on it as far as your grade is concerned. But this is going to go through some of the different kinds of math things that we're going to be needing to do or that we have done. So some of it is rearranging equations. Some of it is fractions. Some of it is scientific notation. Some of it's logs. And so you might think, oh yeah, I totally remember how to do those things. But as you're going through the assessment, you're gonna be like, oh yeah, that's a little bit trickier than I remember. So kind of to help you remind yourself of things that maybe you need to work on, and also to give me a sense of, is this something I need to go a little more step by step with as we go through in class? There is in the practice folder a practice for the math portion. And what that is it's really set up to like help you figure out, how do I type in a fraction? How do I type in something in scientific notation? So that'll help you figure out what the computer wants to see in order to get the right answer. So it's not the computer that is making you wrong as opposed to your understanding. So any questions about that? All right. So I don't plan a big quiz or a test right after we come back. So I want you to be able to enjoy your spring break, but don't forget about chemistry completely, because the more you process it, the more you're going to remember it. Okay, I'm going to recollect your exams here, and I will give those back on Friday when I go over. Okay, so we are going to talk about specific types of solutions. We had talked about the thermodynamics of solutions, and we're going to get a little bit into that today with electrolytes. Well, with not electrolytes, with all kinds of solutions. And we're going to get a little bit into some math. One of the things that we're going to work on Friday is we're going to work on calculating concentration. So I know it's really tempting to just skip out on class on Friday. But if you're not familiar with molality and mole fractions, that's what we're going to be working on Friday as far as concentrations. And that can be really helpful in being successful at the last part of the chapter. So just kind of be aware of that. Okay, so the first thing that I want to talk about are electrolytes. Well, first thing I want to talk about is saturated equilibrium. We mentioned this a little bit on Monday. So equilibrium, remember, is a process where we have two opposite reactions happening at the same time and at the same rate. So in the case of a saturated solution, this is dissolving some particles and then precipitating out particles. So precipitation is the opposite of dissolving. So we use these double arrows here to represent equilibrium. Those are called equilibrium arrows. And when we get to chapter 13, I will be more particular about your using those, but right now just get used to seeing them. And so this applies to saturated solutions when there are some solute particles. So normally we would think of this as being, oh, there's a little bit of the solid on the bottom. We know not all solutions involve a solid in water, but let's just use that as our example. So we had this same image and we said most of these ions were dissolved, but we have this solid particle here. And so we need both of them because we need to have both processes going on. So if I don't have any particles that aren't dissolved, I can't have the forward reaction of dissolving happening. So some solute is constantly dissolving, some is constantly precipitating out. Now, if I were to have this solution and I would add more of this salt, let's say it's sodium chloride, if I add more salt to this, I'm not going to get any more to dissolve. I'm still going to have some dissolving and some precipitating out at the same rate, but no matter how much more salt I add, the concentration is never going to change. And that's a real important aspect of equilibrium, is that because both processes are happening at the same time, our concentration doesn't change. That concentration is going to be determined by what is the dissolved solute, and it's going to be determined by the temperature. So what that means is if I raise the temperature, I could change my concentration. If I lower the temperature, I could change my concentration. But if I'm at that same temperature, the equilibrium will stay the same and the concentration won't change. And this is true for all solubility. So it doesn't have to be an electrolyte like this is showing, but that is the example that is here. May I move on? Okay, so electrolytes. Electrolytes are things that are going to conduct electricity when they're dissolved in water. And so how do they do that? These are substances that will dissolve in water and form ions. So in the words of your book, they undergo a physical or chemical change to produce ions. So obviously this means that anything that is ionic to begin with, if it's dissolving and forming ions, it's going to be an electrolyte. So ionic compounds tend to be electrolytes. Of course, it has to be soluble. So if I'm talking about something that just isn't soluble, this doesn't really apply. But anything that is ionic that I would give you, I'm not going to try and trick you by giving you something insoluble. Anything that is ionic is going to be an electrolyte. So how am I going to recognize something as ionic? Same way we've been doing it all year. I have the formula. What am I looking for? Okay, how are you going to know there's a big difference in electronegativity? I think I heard mumble, 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 metal and non-metal. Yeah, so generally it's going to be a metal and a non-metal. So they're going to have differences in electronegativity because the metals are on one side of the periodic table and the non-metals are on the other side of the periodic table. So there should be a big difference in electronegativity. There are a couple of scenarios where you might have no metals. So just know that there are exceptions to every rule. And one of those is going to involve the ion that we looked at on Monday, ammonium. So ammonium is NH4. And we looked at ammonium nitrate, NH4NO3. So this is both ionic and an electrolyte. Okay, even though there's not a metal. This ammonium is probably the only case that you would see something where there wouldn't be a metal, but it is ionic. Okay, so that's our first big group. We're going to talk about another scenario in just a second. But first I want to address non-electrolytes. Non-electrolytes are going to be covalent. So covalent, they're all attached by covalent bonds. Covalent bonds are very strong. And so they're not going to separate when they get into water. They're going to stick together. How am I going to recognize a covalent molecule? What will it have? Or what will it only have? Non-metals. So aside from something like this that has ammonium in it, if I don't see any metals, I'm looking at something that is a covalent compound. So this is going to be your sugar, this is going to be oil, glycerol, things like that. All right, so there's this middle area that's sort of a, well, except that we're going to get into. So the electrolytes are separating into ions when dissolved. And we said ionic compounds are metals and nonmetals. They do that. But acids also do this, because one of the definitions of an acid is that it dissociates or separates to form hydrogen ions. Now, technically, when we get to chapter 14 or whatever it is, we're going to talk about it's not really an H plus. But for right now, we're just going to keep it simple. Think about, instead of having HA as a molecule, we're going to have an H plus over here, and then everything else in the molecule over there. So it separates with charges, so we get ions. So acids are also electrolytes. We are going to be very interested in this chapter, particularly when we get to the end of the chapter, where we are talking about colligative properties and how many particles are forming. So particles per formula unit. For our ionic compounds, we talked about this on Monday, it's the number of ions that it's going to separate into. So we said that the ammonium nitrate will break into 2 ions, but the NH4 will all stay together because it's held together by what type of bonds? Covalent? Covalent bonds, and covalent bonds are very strong, and the nitrate is held together by covalent bonds, and covalent bonds are very strong. So this isn't going to separate into each individual atom, it's going to separate into the ions. If I look at something like KCl, the potassium and the chloride, that's pretty easy to see. It's going to be 2 things. But whenever I have a polyatomic ion like these here, it's a little bit trickier. So how do I know when it's going to do this? Well, fortunately, last fall, when Dr. Hamilton or Dr. Knapp said, you need to memorize these common ions, you did that. And so you recognize whenever you see NO3, that's a nitrate, right? Just in case you maybe started forgetting that a little bit, you can always review it. But also, whenever there are parentheses around something, usually that's a polyatomic ion. So we have the OH here, the hydroxide. If you had forgotten that hydroxide is a polyatomic ion, the fact that there are parentheses around it would tell you that whole thing sticks together. Okay, so calcium hydroxide is going to break into 1 calcium, 2 hydroxides, for 3 particles per formula unit. Okay. All right. So acids are usually going to break into 2 formula units, but we have different kinds of acids. We have strong acids and we have weak acids. So a strong acid doesn't mean that it is concentrated. It means that it completely separates. And this is a good list to know as well. There are 3 that are really super important. There are 6 common ones. So these 3, hydrochloric, hydrobromic, hydroiodic, right under one another on the periodic table. So they're all together. Hydrochloric we use in lab a lot, right? You've seen that before. We use that to neutralize sodium hydroxide. We also use sulfuric acid, H2SO4, and nitric acid, HNO3. So these 3 are by far the most common acids that we use in lab. We use this one to dissolve the copper. You probably use this one when you were making your aspirin. Okay, they show up over and over again. So we typically will use strong acids in lab. This one is also a strong acid, but it's very oxidizing, and it is also very caustic. It can destroy flesh. So we try not to use that. I'm not even sure we even have any here. If we do, it is a very small amount. So these 3 with the stars next to them, absolutely 100%. You need to know the name, you need to know the formula, you need to know it is strong. So for hydrochloric acid, it's going to break apart into 1 hydrogen and 1 chloride. For nitric acid, it's going to break apart into 1 hydrogen and 1 nitrate. The NO3 is going to stay together. For H2SO4, this one's a little bit tricky. Acids, instead of separating all their ions at once, what they're going to do is 1 hydrogen is going to come off, and when that's done, then the next hydrogen is going to come off. So the first hydrogen is strong and separates completely. And so we just end up with 2 particles. The second one is a little more clingy, hangs out with the sulfate ion, and so isn't involved as much in separation. Okay. For weak acids, we end up having those hydrogen and the other part of the molecule stay together mostly. So if I look at hydrofluoric acid, the one right above chlorine, the fluorine we said is most electronegative of all the elements. So it's very clingy to the electrons. And what that means is the bond between the fluorine and the hydrogen is not as ionic as it is in the others. It's more covalent. And what do we know about covalent bonds? They are strong. So if we have something that instead of being an ionic bond is more of like half ionic, half covalent bond, it's going to be harder to pull that hydrogen away. So when we have hydrofluoric acid, we're going to have some hydrogen ions, but we're not going to have all the hydrogen ions. Okay. So in these pictures here, this is the weak electrolyte in the middle. So you can see these two, let's say they're the acid, stay together, the hydrogen fluoride stay together. And in this one, the hydrogen separate. Now, instead of it being like a 1-to-3 ratio, it's going to be more like a 1 to 1,000 ratio. So it's a pretty big difference in what's separated and what's not. Our strong electrolytes are going to primarily include our ionic compounds, so sodium hydroxide, sodium chloride, and our strong acids, hydrochloric acid is a strong acid. And then our non-electrolytes are things that are only nonmetals. So I have sugar, alcohol, that's ethanol, C2H5, and then an OH on the end, because an OH attached to a carbon is an alcohol. And then oils and fats, also carbon, hydrogen, and oxygen. Okay. So when I have a strong electrolyte, I try to determine the number of particles that we will break it into. We will call that the Van't Hoff factor. Now, technically, the Van't Hoff factor can be something in between, like it is with a weak acid. We're just going to assume it's whatever the whole number is. So for this, we would assume it's 3. Probably if I looked it up on a table, it's more like 2.7. We're not going to get into that. We're just going to say when this dissolves, completely separates, we get 3 particles. So we're just going to keep it simple. If you keep taking chemistry, you'll take physical chemistry, and Dr. Hamilton will go into the exceptions. All right, do we still need this slide? Okay, back to thermodynamics a little bit. This is going to be important for understanding our next group of solutions. So we said that enthalpy, which is our delta H, is favored when it is negative, right? The universe likes things to be more stable, lower in energy. So we want our system to get as low as energy as possible. That's going to be negative delta H. We also said the universe likes to have things be more disordered or more random. Okay? And so we want that to be positive. That's our S. S stands for entropy. So I know that that's kind of a different letter there. You might want to make a special note of remembering that S is entropy. So this is not something I'm going to have you plug into the equation, but this equation helps me see how these two ideas are related. Now remember, our first law of thermodynamics is conservation of energy. It says the energy of the universe can't change. I can move it from place to place. I can move it from the system to the surroundings. I can move it from being light to being heat, from being heat to being electricity. So I can change its forms, but the total energy of the universe is going to remain the same. Okay. So my delta H can be either negative or positive. It's preferred if it's negative, but it can be either. The second law of thermodynamics says that the entropy of the universe is always increasing. Okay, so we're keeping 0 on our energy, but our entropy is always going up. So this is why entropy is sometimes called times arrow, because it is constantly moving in the direction of more disorder. So you might think to yourself, okay, but what about snow? We have water molecules or water vapor, which are disorganized, and then I get these pretty little organized crystals. That's very organized. How could I have something get more organized if the universe wants more disorder? So remember, the universe is both the system and the surroundings. So my system, my water molecules, is getting more disorganized. So what that's telling you is everything around it, the air molecules and other water droplets and things, those are becoming less organized. Okay. So entropy is really a driving factor for reactions. Okay, so putting these two things together, I'm going to call this, or we call this Gibbs free energy. There's another form of free energy, but we'll stick with Gibbs. And basically, a reaction is going to go or be spontaneous if Gibbs free energy is negative. So we want to have a negative Gibbs free energy. So in this equation here, if delta H is negative, and I'm not worried about this, that's going to make delta G negative, right? That makes sense? So a negative delta H we said was favored because it's going to make delta G negative. Now, on the other hand, if we're looking at entropy, we have a minus sign in front of it. So we want entropy to be positive because we're subtracting it off, and that in turn will make this negative. Okay, so that's how those two things fit together. And then the combination of the two determines whether that reaction is spontaneous. Yes, it's going to happen. Or it's not spontaneous. Nope, we've got to change the conditions in order to get this to go. Okay, so technically, the definition of spontaneity is it occurs without external energy, but we said the energy of the universe is constant, so we can't put in external energy. And it does refer to specific conditions, like what's the vapor pressure, what's the temperature, that kind of thing. Okay, so we have this graph over here, and this is showing our, I guess I should have deltas in front of those. The main thing is showing where things are negative and where things are positive. So we said if S is positive, if entropy is positive, it's favored, and if H is negative, so that's this side of the graph, it's favored. So if I have both of those going on, this whole thing is going to be negative. And so it's spontaneous. Doesn't matter what the temperature is. If I've got positive entropy and negative enthalpy, that's a spontaneous reaction. And I guess I should have pointed out this T here. So what do you think this T stands for? Temperature. Okay, now delta H tends to be pretty big in like the kilojoules. S tends to be more like in joules, but it's joules per temperature. What do you think would measure that temperature? What units? Not Celsius, it would be the absolute temperature in Kelvin, which means at room temperature, that's going to be multiplying by almost 300 degrees. So even though this S might only be in tens or hundreds of joules, I'm multiplying it by about 300. So it gets to be about this big. Okay. So temperature is going to make a difference. So if I'm in this area here, what is H, positive or negative? This side of our graph is positive, right? And then S, we're below our axes, so S is going to be negative, right? So this is my not spontaneous, not favored area. Reaction isn't going to go through no matter what the temperature is. What about our other two quadrants? If I'm up here, then I have a positive enthalpy change, an endothermic reaction, but I'm also increasing entropy. So we've got one thing that's favored, one thing that's not favored. So since I'm multiplying by temperature, I want the positive thing, the entropy change, to be really big. So the higher the temperature, the more that factor matters. Okay? So higher temperatures are favored, and we said this is endothermic reactions. All right, so if I dissolve sugar in water, that's an endothermic reaction. What this is telling me is that if I raise the temperature, I can dissolve more sugar. Okay? An endothermic reaction will have more spontaneity at higher temperatures. Okay, So I can dissolve a lot of sugar in water at room temperature. It increases quite a bit as I go up to 100 degrees Celsius. And then we'll talk about later in the semester how it goes up even further beyond that. In contrast, if I have an exothermic reaction, the universe likes that, but it's getting more organized. So this might be our ice freezing example. That's exothermic, but it's organizing. Then I want that to happen when I have lower temperatures, which is why I have to cool things down to form ice. Okay, so an exothermic reaction requires lower temperatures. So we normally think of our dissolving as being endothermic because we normally think, yeah, things are more soluble at higher temperatures, but that isn't always true. So we're going to talk about a whole class of solutions that are not soluble at higher temperatures. But one good example is this, not calcium hydroxide, calcium chloride. So in the winter, we put salt on the roads to melt the ice. Sodium chloride, not much of a difference in the enthalpy, but it's slightly endothermic. Sodium chloride is cheap, not real harmful to the environment, so it gets used a lot. But sometimes they use calcium chloride. Calcium chloride is exothermic. Now, I would know it's exothermic because if I was holding a test tube of water and then dissolved calcium chloride in there, how would that test tube feel? Hot, right? It's going to release heat. So if I'm doing that on the roads, as it's dissolving, it's warming up the ice around it, right? So that's good. And then the other thing is, the cooler it gets, the more soluble it is. So as it cools down, because the weather is cold, I'm able to dissolve more and more and more. Okay, so that's an example of something that would work in the opposite direction. We would be able to dissolve far less calcium chloride at room temperature than we would at the freezing point. All right, can I move on? Okay, so we said when delta H is positive, this is an endothermic reaction, high temperatures are favored. And when delta H is negative, we have lower temperatures favored, and so it is more soluble at lower temperatures. That's the big story to remember. Point all of this in a nutshell. And then I use sugar as my example for the top one, and I use calcium chloride as my example for the bottom one. All right, so the next group or kind of solutions we're going to talk about are those dissolving gases. Now we said gases, where do they fit on our entropy scale? Are they high entropy or low entropy? Highly disordered or highly organized? They're very disordered, they're high entropy, okay? So what that means is that I am going to be in this range for a gas up here. So when I dissolve it, I'm confining that gas to a smaller space. It has less freedom of motion. What is delta S going to be for that gas? Is it going to be more disordered or less disordered? I go from all the gas in the room and I put it into this little bottle with some water. Less disordered. Less disordered means I'm going to have a negative entropy. So the change is going to put me down here. Okay. Okay, I forgot this slide came first, so let's talk about this. So dissolving a gas confines and organizes it. Okay, so delta S is negative. So we're going from a gas, which is, willy-nilly anywhere, to dissolved molecules. That's our change, and that makes the delta S negative. So based on what we just said, if delta S is going to be negative, we need delta H to also be very negative, right? We have to counteract that. We have to have that big negative delta H in front of the minus delta ST. These things are temperature dependent. So if delta H is negative or it's exothermic, what's favored? Higher temperatures or lower temperatures? Lower temperatures, right? That's what the point of the last slide was. So if I look at this graph, what I'm showing is the solubility of these gases starts off higher and gets lower as the temperature increases. So unlike most solids, most ionic compounds, the graph would go in the other direction. For gases, they're less soluble at higher temperatures. That solubility is going to depend on inner particle forces, and most gases tend to be nonpolar, which means what's their dominant inner particle force? Dispersion forces, okay? And I have fewer dispersion forces if I have very light molecules or atoms with very few electrons. So notice helium's way down here. There's only 2 electrons, only 1 atom. It's teeny tiny. This is the smallest of all possible gases. And so it has very low solubility. If I have nitrogen, it's diatomic, so it's going to be a little bit bigger. Oxygen is up there, also diatomic, but by the time I get to methane, that has 5 atoms. And so it's got more electrons and it's got more things that can change its shape and allow it to be a little bit more polar. So when I looked at this, I noticed carbon monoxide. I said, well, carbon monoxide ought to be a polar molecule. Why isn't this the most soluble? So I tried looking it up, and of course the internet was like, oh, surely you mean carbon dioxide, not carbon monoxide. So the internet was not. So I went to Dr. Hamilton. He's our physical chemist. So this is the kind of thing that he looks at. And I asked him about it, and he wasn't sure either. But he told me, you know, it's a really good thing that carbon dioxide isn't, or carbon monoxide isn't very soluble because it's so bad for us. It's toxic. And so we decided between the two of us that the reason why carbon monoxide is less soluble than oxygen is because God loves us. All right. Okay, so we said dissolving gases is exothermic, and what this means is that gases are more soluble at lower temperatures. So you kind of instinctively know this because if you have, say, a 2-liter bottle of soda, you don't finish it, you want to save some for later, you don't leave it out, you put it in the refrigerator. Putting it in the refrigerator keeps that carbon dioxide dissolved in the soda. All right, are we good on this slide? Okay, so here is our first calculation, Henry's law. So they use C for solubility because we're already using S for entropy. The little subscript G just means whichever gas we're talking about. So I would change that G to CO2 if I was talking about carbon dioxide. Our old book used S for the solubility, so you may see old slides or documents that I have on campus that have an S. That is why I'm trying to stick with what you're seeing in your book, though. K is a constant, and so that means that this this number will be the same for the same gas. Every time I use carbon dioxide, it's going to be this, but it's temperature dependent. So normally, if you look this up on a table, this is what K is at 20 degrees Celsius or 25, close to room temperature. And then we see the notation P with a chemical down below. That is our partial pressure. So remember, since gases are not touching one another, they don't really know what other gases are there. So it's as if they're alone in the room, even if there are other gases floating around. So we're only concerned about the gas we're trying to dissolve. So when we put the pressure in here, we're not going to put atmospheric pressure. We're not going to put 1.0 because the atmosphere is made up of several different gases. Now, one of the things we are going to be looking at in the coming chapters is a lot of different graphs. We've looked at a few in the last couple of chapters, and we're going to keep seeing these. But more and more, we're going to be looking at how equations are related to those graphs, particularly in our next chapter on kinetics. And so we want to be able to look at an equation and kind of have in mind, what do I expect to see, so that we can relate the equation to the graph, because you're going to have to decide which graphs go with which equations. So let's take a look at this. We have here CG is equal to KPG. So I'm going to say C is our Y. I'm going to put that on our vertical axis, and P is our X. Now, I don't have K on an axis because it's constant. It stays the same. Okay. So if I have the graph like this, do I expect this to be a straight line? Yes. So you probably remember y equals mx plus b. That's the equation of a straight line. So this is y equals mx, and our b is 0. Okay. So what that means is that if I have no vapor of carbon dioxide, I can't dissolve carbon dioxide. So it just intercepts at 0. Okay. So it's going to start down here. Is this going to be an uphill graph or a downhill graph?
Does it depend on K?
It does depend on K. So let's think about what K says. K is the solubility at a different temperature. Is it possible to have a negative solubility? Is it possible to have a negative concentration? No. So since I can't have a negative concentration, K has to be positive. So if K is positive, what's that going to tell me about the graph? It's going to be an uphill graph. Okay, now we don't know what that slope is going to be, but we should expect this to be a straight line going up. Uphill. All right, so we are going to try calculating with this. I think that's what's on the next slide. Oh, no, we have a picture first. Sorry. Okay, so we talked about equilibrium before, and we talked about how we have both the dissolving and precipitating happening at the same time. So in this scenario here, we have equilibrium. Now I said that equilibrium technically applies to closed systems. So we've got a lid on here. This is a piston. So the piston has a plunger that can slide up and down as the pressure changes. So I can increase the pressure by pushing down, or if I have more pressure inside, it can push it up. And so right now I have an equilibrium established where I have these molecules are dissolved, and then at the surface, some of these are going to be evaporating, but then some of the molecules that are up here are going to start dissolving. Okay, so I have an equilibrium because I have the same number doing both. If I increase the pressure, I should increase my solubility. And so now I see I have more dissolving than I have evaporating. And so this is the not equilibrium. It's not equal up and down. But after a certain amount of time, I'm going to dissolve enough of that gas that I'm going to restore equilibrium. And so I'll have the same numbers dissolving and evaporating at the same time. So notice that as I increase the pressure going from right to left, there are more dissolved particles there. Higher pressures are increasing the solubility of the gas. But what's dissolving? The molecules that are in the vapor above, those are the molecules that are down below. Only the pressure of these molecules affects how many are dissolved. If I were to add, say, red molecules or neon molecules, that would not affect how many of the blue molecules dissolve. Okay, so let's try a calculation. The left-hand side was on our previous slide. So if you've been copying it down, you've already copied that. That's just defining what our variables are. On the right-hand side, we're going to have some information. So at 30 degrees Celsius, we have a Henry's constant of 1.2 times 10 to the minus 3 molar per atmosphere. Okay, so that's telling us how much oxygen could dissolve if I had 1 atmosphere of oxygen. And we're going to look at some fish. Now, fish need oxygen just like we do. They're animals, but they don't have lungs. They have gills, and so they have to absorb that air through the gills from dissolved water, so or dissolved oxygen in the water. So the water enters, and then their bodies are able to pull the dissolved oxygen out of the water. So they need a certain concentration of that in order for it to get absorbed into their bloodstream and remain healthy. So the oxygen concentration they need is 2.3 times 10 to the minus 4 molar. Now, if I'm at normal atmospheric conditions, then I have 1 atmosphere of air, but the pressure of the oxygen is going to depend on what percent of the air is oxygen. So about 80% of the air is nitrogen. It's really closer to 78% if I have completely dry air, there's no evaporated water in it. And for the oxygen, it's closer to 21%. So let's assume we have dry air and we have 21% oxygen. Is this going to be enough oxygen for the fish to remain healthy? So what we're going to do is our K is up here, and then our partial pressure, this was already calculated for us, 0.21 right here. So we're going to plug those 2 numbers in. And we're going to get this. So my calculator does this sometimes to me. I enter things in scientific notation and it spits it out in not scientific notation. And then I have to think about, oh gosh, what is that number in scientific notation? So remember, in order to change it to scientific notation, we're going to move that decimal. We're going to move it until it is after the first non-zero. So when I move to the right, this is going to become a negative exponent. So -1, -2, -3, -4. So this is 2.5 times 10 to the -4. So is this high enough oxygen for our fish? Yeah, so that works out well for the fish. But remember the percent, oh yeah. Partial pressure is atmospheres, and that cancels the 18 up there. And then this should be molarity. All right, so remember that that partial pressure is going to depend on a couple of different things. So I said, what if it's completely dry air? But if I'm over a lake or a river or an ocean, there's probably some water vapor in there, which means the percentage of the air that's actually oxygen is lower than that. And then it's also going to depend on what the normal air pressure is. And so we've talked before about how around Georgetown, we're above sea level. And so we tend to be a little bit below. Now we're at like 0.998, so it's pretty darn close. But if I were way up in the mountains in a mountain stream, then the air pressure might be a little bit lower. So I might be being knocked down to 0.17, 0.15 pressure for the oxygen. This is why it's harder to breathe when you're in the mountains. The partial pressure of the oxygen is lower. And so what gets absorbed into your lungs is less, okay? So what can happen for fish is if the temperature gets too high, then there's not enough oxygen in the air and they can get killed off. And so we call this thermal pollution. So it's not that there's a chemical in the air that's bad for the fish, The problem is that the temperature of the water is so high, it's not dissolving enough oxygen. So there's an obvious connection for this to climate change, because as ocean water temperatures rise, or as the temperatures of the atmosphere rise, this is raising the temperature of lakes and ponds and things like that, and making less oxygen dissolved in the water. This also has an impact on the carbon dioxide, because some carbon dioxide from the atmosphere is absorbed into the ocean, and that's how nature mitigates the amount of carbon dioxide. But as the temperatures rise, less of that can be dissolved. A more timely sort of example, one that you can see in real time, would be when you have some kind of an energy plant. You most often see this scenario with like a thermonuclear plant, where you're going to have energy being produced and your machinery is getting hot and things like that. And so you're going to run cool water around stuff. It's not mixing with your nuclear power or anything. It's just water. It's clean water, but it's absorbing the heat. So it's getting warmer. Well, they're not just going to leave that running around in their factory. They have to put it somewhere. So sometimes they'll have ponds where it just goes out into the pond, and then the heat dissipates into the atmosphere, and then they'll bring in cooler water to continue with the process. But they can't generally keep fish in these ponds, because generally the water temperature is too high for this. You don't want to have this go directly into a river, because you might kill the fish in the river. Sometimes they will use oceans. Why might it be okay to do it in an ocean, but not a river or a pond? Larger body of water. Yeah, since you have a larger body of water, that small amount of hot water, or warm water that you're putting into the ocean does not cause a huge temperature change. But if it happens too rapidly, you can get fish kills, which is what you're seeing in the picture there, where too much hot or warm water was put in and caused the fish to be killed off. Okay, on Friday, we'll start by talking about which gases dissolve the most, and talking a little bit more about carbon dioxide. And then we'll get into some calculations on concentrations. And I will give you your tests back. Tomorrow,